Hey everyone, welcome back to The Explainer. We're going on a seriously fascinating under-the-hood journey today. We're going to look at exactly how software words, specifically Verilog syntax, translate directly into physical hardware reality. Because when we write this kind of code, we're not just writing abstract instructions, we are quite literally drawing wires. So let me ask you something. Have you ever written a line of code that accidentally erased a piece of physical hardware? It sounds completely like science fiction, right? But in the world of hardware description languages, a single misplaced character can literally make a silicon component just disappear during compilation. Today, we're looking at exactly how compilers interpret our syntax to build, or in some cases, destroy the physical circuits we rely on. Okay, let's dive right into this. Here is our roadmap for the breakdown. We'll explore the heart of memory, blocking versus non-blocking assignments, combinational versus sequential logic, the reset button, and finally we'll wrap it all up by building shift registers.
All right, kicking things off with Section 1, the heart of memory.
Before we can go off and build massive systems, we really need to understand foundational blocks like the gated delatch circuit. When we write Verilog code for memory, we aren't just writing sequential instructions for some standard processor to execute line by line. We are essentially asking the synthesis tool to wire this exact physical circuit for us. Notice the crisscrossing lines there. Those are feedback loops. This specific design creates a latch that's synthesized to maintain the value of Q whenever the clock signal drops to 0. It physically traps the data, holding it securely right there in memory. Now, let's look at the edge-triggered D flip-flop. Notice the specific keyword sitting right there in the parentheses, posed. This isn't just some logical if statement. This is how we command the hardware to trigger its action exactly and only on the positive edge of the clock signal. It's a strict physical constraint, but it's written simply as a software word. Moving right along to Section 2, blocking and non-blocking assignments. Or as I like to think of it, where syntax equals wires. So this is the core conflict we really need to wrap our heads around today. Notice the simple equal sign in this code snippet? That is what we call a blocking assignment. The Verilog compiler evaluates these statements sequentially, in the exact order they're written, line by line. So Q1 gets the value of D, and then immediately after that, Q2 gets that newly updated value of Q1. Now, in a normal programming language like Python or C, this makes perfect logical sense. But in hardware, this simple little equal sign is about to cause a massive structural headache. And this brilliantly illustrates the physical fallout of that equals sign. Because Q2 evaluates after Q1 has already updated, Q2 essentially just copies the original input D. So instead of that beautiful cascaded sequence we actually wanted, where one flip-flop hands its data off to the next, the synthesized hardware throws us two parallel flip-flops receiving the exact same data at the exact same time. Not what we wanted. Remember my question earlier about accidentally erasing hardware? Well, here's the big reveal. Because we just created a totally redundant flip-flop that operates identically to the first one, a synthesis tool is going to analyze this, realize it's completely inefficient, and likely just delete one of these flip-flops as a background optimization step. No joke, our incorrect use of syntax literally caused the compiler to optimize away the physical hardware we thought we were building. Unbelievable, right? So how do we stop our hardware from pulling a disappearing act? Simple. We use the non-blocking assignment operator. That's the less than or equal to sign. With non-blocking assignments, all statements in the block are evaluated using the values the variables had when the block was first entered. Then, everything changes to its new value concurrently, at the exact same time at the very end of the block. Boom! By just swapping an equal sign for a less than or equal to sign, we dramatically change the physical wiring. This syntax physically wires the cascaded connection we actually intended all along. Because Q2 looks at the old value of Q1 before Q1 gets overwritten by D, it creates a true chain. The first flip-flop feeds its data directly into the second one, perfectly implementing a shift register. Honestly, if you take away just one thing from this explainer today, absolutely memorize this distinction. A blocking assignment uses a regular equal sign, it executes line by line, and it is specifically designed for combinational circuits. A non-blocking assignment uses the less than or equal to sign, it executes all at once concurrently, and it is strictly designed for sequential circuits. You know, those circuits where the outputs depend heavily on past behavior combined with present input. Which brings us nicely to Section 3, combinational versus sequential logic. Let's actually apply these rules. Let's see exactly what happens when we mix these rules up. Compare these two blocks of code attempting to write the exact same function. On the left, we have blocking assignments appropriately describing a combinational logic function, perfect. But on the right, we've mistakenly used non-blocking assignments. Because the non-blocking assignment evaluates concurrently, that second line doesn't see the update from the first line. The result? Instead of a clean logic function, the synthesis tool builds this disastrous and/or circuit where the OR gate actually feeds back into itself. Just a complete mess.
Let me just state this loud and clear as a cardinal rule of hardware design. To build a sequential circuit, you absolutely must use non-blocking assignments. And conversely, stick strictly to blocking assignments to describe your combinational circuits. Using the wrong syntax here doesn't just give you a tiny software bug. It wires up entirely unexpected, completely incorrect hardware. All right, on to section 4, the reset button, how to clear our memory safely. Now that we actually know how to wire memory without accidentally erasing it, we kind of need a way to intentionally clear it, right? Notice how a single word completely alters the behavior here. Focus on the sensitivity list. That's the part in parentheses right after always at. On the left, our asynchronous reset includes the specific trigger negative reset n. But on the right, the synchronous reset code lacks that entirely, meaning it triggers strictly on the positive edge of the clock and nothing else.
So what does that actually mean when the silicon hits the road? Well, an asynchronous active low reset forces the output to 0 immediately. The exact microsecond the reset signal drops to 0, totally independent of what the clock is doing. A synchronous reset, on the other hand, sees that 0 but patiently waits for the very next positive clock edge to arrive before it acts to clear the output. And this synchronous behavior actually forces the compiler to generate a circuit with an extra AND gate built right into it, taking up physical real estate on the silicon just to manage that strict clock dependence.
Finally, section 5. Building shift registers. Let's scale things up a bit. We've got the foundations down now. Flip-flops, assignments, resets. Now we bring it all together. Here we have the specs for a parallel access shift register. By just slapping a simple 2-to-1 multiplexer onto the input of our D flip-flops, we give each memory unit a choice. If our selector signal is set to 0, the multiplexer pulls data from the preceding flip-flop, running smoothly in shift register mode. But if the selectors flip to 1, the multiplexer grabs an external input, allowing us to parallel load fresh data all at once. And because this is a sequential circuit wired perfectly with non-blocking assignments, absolutely every single action occurs dependably right on the positive edge of the clock. We've just seen how non-blocking syntax acts as the absolute perfect wire for building shift registers to move data sequentially. But I want to leave you with a thought. If this simple, concurrent, less than or equal to sign strings memory together so effortlessly, what kind of absolute powerhouse counting machines could we build next by simply introducing an adder into this feedback loop? Well, I'll tell you, that is the exact gateway to building synchronous counters, opening up a whole new world of complex hardware design for us to explore. Thanks so much for joining me for this explainer. Keep exploring those circuits, and I'll catch you next time.